Hi everyone, I'll be presenting our paper on optimal anytime regret with two experts. This is work done by Nick Harvey, myself, at Perkins, and Sikander Randhawa. So we're going to be looking at the classic problem of prediction with expert advice. In this problem, there is an algorithm A that wants to make predictions given advice by a panel of experts. In addition, there is an adversary B who will set the cost of each of the experts. The game proceeds as follows. At each time t, the algorithm chooses a probability vector over the n experts. So for example, 0.5, 0.3, 0.2, and 0. The adversary then sets the cost on each of the experts. Here, the adversary is all powerful and he can pick the cost knowing all information, including the future. In this example, he sets cost 1 for the first two experts and cost 0 for the last two experts. The algorithm then incurs cost, which is equal to the inner product between the cost vector and the probability vector, which in this case is equal to 0.8. The cost vector is then revealed to the algorithm. The objective is to minimize a quantity known as regret, which is defined to be the cost of the algorithm minus the cost of the single best expert in hindsight. One thing I'd like to mention is that the problem doesn't contain any randomness. The algorithm is deterministic, and so the sequence of cost vectors can also be predetermined by the adversary. The expert's problem has a number of different models. One classical model is a fixed time model where we assume that the algorithm is provided with time horizon t in advance, and its goal is to minimize the regret only at that time. Pictorially, we have this orange benchmark curve, and the algorithm's regret is only guaranteed to meet this benchmark at the final time t. You could ask whether that is reasonable. It is really saying that the algorithm will only have a good track record at one point in time. A more stringent model is the anytime model, where the predictions must continue indefinitely. In other words, the algorithm's regret must be small at all points in time. Pictorially, this means that the regret must always be below the orange benchmark curve. There is another setting which interpolates between the two models, and that is the random stopping time model. Here, the stopping time is unknown to the algorithm, but it is drawn from a distribution which is known to the algorithm. So let's go over some history of the problem, and I will state all the results after they have been normalized by square root t. In the fixed time setting, Thomas Cover, the information theorist at Stanford, showed that for two experts, the optimal regret is 1 over square root 2 pi. This is both the upper bound and the lower bound. When n is very large, it is known that the optimal regret is square root 1/2 ln n. And this is achieved with the famous multiplicative weights update algorithm. Any lower bound for the fixed time setting carries over to the anytime setting, so we also have the square root 1/2 ln n lower bound in the anytime setting as well. In terms of upper bound, a well-tuned multiplicative weights update algorithm can obtain square root ln n for any value of n. This was previously the best result for all values of n. For n equals 2, Liaw and Triperi also showed a lower bound of square root 1 over pi in the anytime setting. There's also been some additional work in the fixed time setting. For 3 experts, the optimal regret is known to be square root 8 over 9 pi. And for 4 experts, the optimal regret is square root pi over 8. So our main result is an optimal algorithm in anytime setting for 2 experts. And we show that the optimal regret is equal to gamma over 2, where gamma is a constant I will explain later. Numerically, the value of this constant is about 0.653. And this is the first tight result in the anytime setting. I want to stress that the important thing is not the numeric value of the constant. The important thing here is to understand what are the techniques that might be required to develop optimal algorithms. So I'll talk briefly about the various techniques that have been used. Our result in the n equals 4 case for fixed time regret both make use of ideas from stochastic calculus. Some of these upper bounds are based on the multiplicative weights update algorithm. And for n equals 2 and n equals 3, in the fixed time regret setting, they make some nice connections with random walks. So formally, our result is as follows. For n equals 2 experts, we show that there is an algorithm that guarantees against all adversaries that the regret is bounded above by gamma square root t over 2. And this bound holds for all points in time. So what is gamma? Gamma is defined in a somewhat strange way. It is defined as a unique positive root of the function m0 of x squared over 2, where m0 of x is also defined in a somewhat strange way. m0 is defined as e to the x minus square root pi x times earthly of square root x. And here, error-free is the imaginary error function. So at first glance, M0 might seem like a bizarre function, but it is an example of a confluent hypergeometric function, and these functions often appear when looking at PDEs or Brownian motion or random walks. And since regret is often closely related to random walks, it's not terribly surprising that confluent hypergeometric functions actually make an appearance. Perhaps surprisingly, we are also able to get a matching lower bound. We also show that for any algorithm and any positive epsilon, we can design an adversary that forces the regret to be at least gamma minus epsilon over 2 square root t, at least for some time t. Hence, we can get arbitrarily close to the above upper bound. Now, for the rest of my talk, I will talk about some of the ideas which go into designing the algorithm. So here is an overview of our approach. We will start with a discrete regret problem, and by analogy, we will come up with a continuous regret problem. This continuous viewpoint will allow us to utilize tools from stochastic calculus, and in particular, Ito's formula. In turn, this will expose a connection between the regret and the backward seed equation, and with this, we will obtain an optimal continuous solution. Once we have the optimal continuous solution, we will be able to come up with an optimal discrete solution using a discretized version of Ito's formula and the backward seed equation. So let's go back to step 1 a little bit and talk a little bit more about the discrete regret problem. In particular, I want to make some assumptions and simplifications which will make our lives easier. The first simplification I want to make is that we will design an algorithm that depends only on the time t and the gap g. Here, the gap is defined as the cost of the worst expert minus the cost of the best expert. In other words, the algorithm does not care about the realized cost. It only cares about the difference in the cost between the two experts. And this allows us to specify the algorithm with a bivariate function PTG, where PTG denotes the mass on the worst expert. So here is a pseudocode again. At each time t, the algorithm will only remember the gap from the previous time t minus 1. The algorithm now chooses a probability vector whose coordinates are p and 1 minus p, or it could be swapped depending on which of the coordinates actually correspond to the worst expert. We will also make the assumption that the adversary is actually randomized, and it chooses one expert uniformly at random to get cost 1, while the other expert gets cost 0. So in the pseudocode, this means that the cost vector is either 0, 1 or 1, 0 uniformly at random. This also means that the change in the gap is plus or minus 1 with equal probability. And finally, the algorithm incurs some cost, and the cost vector is revealed to the algorithm. So here is a gap process, and observe that the gap process is evolving as a random walk, or more specifically, a reflected random walk, since the gap may not go negative. Finally, it follows from an easy calculation that under these assumptions, we can write the change in regret at time t to be equal to PDG times the change in the gap at time t. In other words, if the worst expert gets a cost, then the gap increases by 1 and the regret increases by PDG. And conversely, if the best expert gets a cost, then this will decrease the gap by 1 and the regret decreases by PDG. So let me briefly summarize. Our goal is to design a function PTG satisfying a couple of constraints. First, PTG must be in 0, 1 so that it is a valid strategy, and PT0 must be equal to 0.5. And this means that when both experts have the same cost, we put 50-50 mass on each of them. Our objective is to ensure that the regret is almost surely small at all points in time. And let's remember that the gap process is evolving as a random walk. One quick observation I will make is that the regret process can be seen as a discrete integral of P against the gap G. And we will come back to this observation very shortly. So that's all I want to say about the discrete regret problem for now. Let's see how to get an analogous continuous regret problem. First, let's quickly review the discrete problem again. Here, our goal is to design a function PTG, which makes the regret, which is a discrete integral, almost surely small. So to move to the continuous case, we will imagine that the gap process is no longer a discrete process, but actually a continuous process. So now our goal is to design a function PTG, which makes the continuous regret almost surely small, and ideally something like square root t. Here, the continuous regret is defined as the integral of P integrated against the continuous process G. And so what should the process G be? In a discrete case, G was a random walk. Hence, in the continuous case, it is natural to evolve G as a Brownian motion, or more precisely, reflected Brownian motion, since the gap cannot go negative. Okay, so now observe that the continuous regret is actually a stochastic integral of P with respect to Brownian motion. And one nice thing is that stochastic integration is very well understood, and there are many books written on the topic. Finally, in the discrete setting, we had a couple of constraints on how we can design PTG. The first constraint is that it must be between 0 and 1. The second constraint is that PT0 must be a half. In the continuous case, we will enforce these constraints as well. Okay, so now we've defined the continuous regret problem. Let's see how to actually solve it. And to do this, we will make use of a fundamental tool in stochastic calculus known as Ito's formula, and we'll see that the backwards heat equation plays an important role in designing the optimal algorithm. Here is Ito's formula, which is due to Kiyoshi Ito. Given a function r, Ito's formula states that r, evaluated at some time t, and the position of Brownian motion at time t, is equal to a stochastic integral involving a g derivative of r integrated against Brownian motion, plus the classic integral of partial t of r, plus 1/2 partial gg of r, integrated against time. So initially, this might look like a bit of a mess, but if you stare at this a bit, it should actually be reminiscent of the fundamental theorem of calculus. In fact, the only difference between Ito's formula and classical calculus is the second partial of r in the second integral. So really, you should think of Ito's formula as a stochastic analog of the fundamental theorem of calculus, but with a correction term that deals with the fact that we are now integrating against Brownian motion. So let's go back to our problem. Remember that we are trying to design a function PTG, which makes the continuous regret small. So now let's try to use our new tool. Ito's formula states that the function r is equal to some stochastic integral plus a classical integral, which seems like a little bit of a mess. But let's focus on the stochastic integral first. Note that the continuous regret is defined as a stochastic integral of some function integrated against Brownian motion. But Ito's formula also contains a stochastic integral of a function integrated against Brownian motion. So here's an idea. Why don't we try to enforce the function Ito's formula to satisfy the constraints that its first derivatives must be between 0 and 1, and when the gap is 0, the first derivative must also be equal to 0.5. And this means we can define the stochastic integral appearing in the Ito's formula as a continuous regret. But what about the other integral, which appears to be a little bit messy? And the key idea is that we will try to find a function r so that the integrand is exactly 0. And this will allow us to completely ignore this second part. Okay, so in other words, if we throw it away, we have that the function r is exactly the continuous regret. And this is assuming that partial t plus 1/2 partial gg of r is identically 0. In fact, this identity is extremely well known in the PDE and probability literature, and it has a name. It is called the backwards heat equation. Okay, so to summarize, if our algorithm is defined as the g derivative of some function r, where r satisfies the backwards heat equation and some minor constraints, then r is exactly the continuous regret. And from now on, I will refer to r as a potential function because it is telling us exactly how the regret is evolving. Okay, so really this is the equation that you need to remember, is that the function r is giving us the continuous regret. Now we can start to set up a PDE, which we will try to solve to obtain an algorithm. The first condition is just a backwards heat equation. The second condition is that we assume that when the gap is 0, we put 0.5 mass on each of the experts. The third condition is that the strategy must be between 0 and 1. This just enforces it to be a valid algorithm. Under these assumptions, we have that the continuous regret is given by the function r. So at this point, the PDE system actually has many solutions, including the rather silly one, which sets PTG to be the constant function 0.5. So the issue is that we haven't even enforced the natural condition that PTG should be decreasing in G. Surely we should put less mass on an expert if it continues to perform poorly. We will take an extreme form of this idea and put 0 mass on an expert that is sufficiently poor. Formally, we will put zero mass on the expert when the gap passes a square root t boundary. And it turns out that we can actually find the optimal constant for the square root t boundary, and it happens to be exactly the gamma that appears in our main theorem. Okay, so now we have a PDE to solve, and we can actually get a closed form solution for this PDE. Here, I've plotted the solutions, and you will note that P does satisfy the boundary conditions. So when the gap is 0, which is at the blue boundary in the picture on the right, the value of P is exactly 0.5. And at the gamma square root t boundary, the value of P is exactly 0. And on the left is a plot of R, which is the integral of P. It turns out that these solutions are scale invariant and can be normalized. Here are the normalized plots in one dimension, and the plot of R on the left is scaled down by square root t. Notice that it is initially increasing and eventually becomes flat. In fact, it becomes flat at exactly the gamma square root t boundary, and the value there is exactly gamma square root t over 2. And this allows us to conclude that the continuous regret is bounded above by gamma square root t over 2. Okay, so now we have the optimal continuous solution. Let's see how to go back to the optimal discrete solution. And here we will use a discretized version of Ito's formula and see how the discretized backwards heat equation plays a role. So let's start with the continuous setting again. We notice that using Ito's formula allows us to express the function R as a continuous regret of some algorithm, plus some other stuff. It turns out that there is a discrete version of Ito's formula, which more or less says the same thing, but in a discrete time. In other words, given a function R, we can write it as a discrete integral of its discrete derivative, integrated against the gap, plus some other stuff. So the only difference between the two formulas are that the continuous derivatives are now replaced by discrete derivatives. And by taking the discrete derivative of R as our algorithm, the discrete integral now becomes the regret. Now in continuous time, we made it a constraint to enforce the backwards heat equation. Here, we might consider enforcing a discrete backwards heat equation and trying to set up a discrete PDE to solve. And that might work, but we are actually going to take a different route. Since we already have an optimal potential function for the continuous case, let's try to plug it in and maybe cross our fingers. And what we are really hoping for is that maybe the discretization error is small enough that it doesn't really affect anything. And it turns out a miracle happens. And here's the miracle. The discrete backward heat equation here turns out to be non-negative. And this turns out to be exactly the direction we want because it allows us to bound the entire right-hand side by the regret. Or in other words, the potential function is an upper bound on the regret. And we already established an upper bound of the potential function. And so that's it. We now have an algorithm for the discrete regret problem with regret at most gamma square root t over 2. I'd like to conclude by showing the actual algorithm, and it turns out to be very simple. First, the algorithm initializes the gap to be 0. Then at each time step, the algorithm computes PTG, which is defined as the following discrete derivative. Then the algorithm computes the probability vector xt, which is p and 1 minus p, or perhaps flipped around, depending on which coordinate is actually the best expert. Next, the adversary chooses a cost vector. And during my talk, I made some assumptions on what the cost vector is, but it turns out that we can easily deal with the case where each of the coordinates are between 0 and 1, and not just 0 or 1. Then the algorithm incurs some cost, and the cost is revealed to the algorithm so that it can recompute the gap. So we can run through the algorithm. So initially, the gap is 0, and here the regret is upper bounded by R00, which in turn is upper bounded by, well, 0. Then the algorithm computes the partial derivative at time 1 and gap 0, which turns out to be 0.5. Then the gap goes up, and the regret is now bounded above by the potential function R11, which is upper bounded by gamma over 2 times square root of 1. And now the algorithm computes a partial derivative at time 2 and gap 1, and the process continues. Okay, so let me just conclude. In this paper, we designed the optimal 2 expert algorithm, and we showed that it has regret at most gamma square root t over 2. And this bound holds for all times. We can also show that this bound is tight. The algorithm was designed by considering a continuous analog of the problem, and in fact, the continuous problem was amenable to tools from stochastic calculus. Let me mention some open problems in future directions. One direction that we think might be interesting to explore is whether or not our results are connected to finance in some way. In particular, you can say that we designed the optimal hedging strategy for two experts using ideas of stochastic calculus. And in finance, the optimal hedging strategy for option pricing is also derived from stochastic calculus. So perhaps there is some unexplored connection along these lines. One other direction that is interesting to explore is how some of these techniques may be used in other problems in online learning. So that's all I have, and thanks for listening.